So welcome everyone, and as I said, I'm presenting about the NFDI4Earth. The NFDI, I think I don't have to explain this in too much detail in this audience here, is one of the consortia of the National Research Data Infrastructure, which has been established just a couple of years ago when the German government discovered it needs to do something about this digital stuff that's going on and is likely here to stay. And the NFDI4Earth is one of 28 now, I think, consortia, which were funded in 3 rounds. The 3rd round is now closed, so we are in full swing basically now. So just very brief outline of this talk, because as Maria said, we are 2 persons today. So I will talk about the NFDI4Earth, give a little bit an overview what it is. I will just very briefly touch on Jupyter Hubs, because this is a little bit part of our sort of cooperation between the NFDI4Earth and HeFDI, because we have Tamara as sort of a little bit of connection between our 2 initiatives here. And I give a research data management example from an NFDI pilot. I will present you what a pilot is, and then you will know what it is, and I will give you this example, and Tamara will then give a specific example also from data science and why, and this will emphasize also why NFDI and HeFDI are such important and vital initiatives. So the official start of the NFDI was on the 1st of October of 2021, so almost 2 years ago, but the full start with everyone on board and so on was about January to March 2022. So we are now going since about 1.5 years. And if I would need to describe the NFDI4Earth or the NFDI in general in the tiniest nutshell possible, I think it is about making data fair, so findable, accessible, interoperable, and reusable. And I'm pretty sure you've all heard about these principles, but this is really at the heart and at the core of all the NFDIs, and everything else sort of orbits around these very important and core principles here. But the Earth System Sciences is a very broad field, and we are very proud within the NFDI4Earth that we were able to bring together all the various domains in the Earth sciences. So for example, geosphere, the atmosphere, biosphere, hydrosphere, and so on, and all the way up also to include meteorites, other planets, and so on. And so this is also why we are the second largest consortia, so we are one of the largest. And it was quite a challenge getting all under one hat, but we managed, and we are, I said, quite proud of this. And the idea is now to go from local processes to global challenges. And here's where all the data come in. Because all of us, all the researchers in the various Earth science systems domains work on maybe soil science, on climate, on weather, on marine sciences, on the rocks beneath them, on maybe the Earth dynamo or something like that. And we have all this data of maybe one location or one region. And what we want to do is bring all these data together so that these can be accessed through one web page. And by this, we might be able to address global challenges. Maybe if there's a drought or something like that, then we have all the data available for this region to address this kind of problem that might be emerging there. And do this by, of course, observing, measuring, modeling, analyzing, and predicting the Earth system. So we bring in from all the various domains of what is possible of accessing data into the NFDI here. And then one very often funny part is, of course, we are the NFDI4Earth and the NFDI, and there's this national in there. And there's sometimes a confusion, how can this be national? Because we are international community, we are an international science, and of course we are. And the big thing about the NFDI and this national aspect is that we are not, as is very often in academia in Germany, restricted to states, but we try to do this on this national level. And this is, of course, then also where HeFDI and these kind of state consortia come in as very important, because they have this local integration, as Maria already said, with the researchers in university and research institutions, and the NFDI itself, the national branch, if you want, is on this level where we try to bring everything together. And the NFDI itself is then an element of the European Open Science Cloud, because every country of EOSC has to bring something to the table, and Germany brings the NFDI to the table. So this is how this sort of works here. Now, who are we? We have 58 institutions. I think we are now 60 actually. We start with 58, and you can see from all over Germany here. And we are not restricted to university or something like that. We have universities, research organizations, infrastructure providers, governmental institutions, scientific associations, and networks. And we started this in 2018 as an open consortium. And now, as said, in 2021, or in 22, we got the funding, and 2021, we started this entire NFDI4Earth here. And we are constantly growing and including additional stakeholders here, and as said, from all the different data providers. So how do we start in Earth System Sciences? So we have data from different sources, and these sources are quite heterogeneous. And this, well, actually is the biggest obstacle and the biggest challenge, and actually also the justification why we are here as NFDI4Earth, because all these sources are so different, so heterogeneous. Some have different levels of openness. Some are completely closed, some are completely open, some may want some money or some subscriptions, and so on. These different infrastructures, they have very often demanding models. They have maybe data-intensive applications. So maybe we need to share some common data centers to calculate these models, to operate these models. The entire idea of the NFDI4Earth is to have a positive attitude towards openness, fair, that's what I said before, and of course we want to be collaborative. And we start with established data repositories, and then we have again the challenge of, for example, getting together several standards for interoperability into a single web interface, basically. So we started by trying and collecting data services, and we found about 150 data services. So again, a large heterogeneity here. With all activities related to your system sciences, only a few of these sustainable. So very often these are small databases, maybe local to a university, maybe local to a computer of an individual researchers, but of very high value. And we need to collect these and put these into something like maybe, say, a knowledge hub or something like this that can then be accessed through a web interface so that they really find all these important resources here. We have a very high data heterogeneity in quality, curation, levels, licenses, semantics, and so on. And we need to find ways to homogenize these or find mapping tools so that if we want to access various databases, we can do this through one single tool and not need to rely on a lot of different tools. There are different data cultures, of course, and velocities towards FAIR. This is also a challenge we need to address. There's incomplete support along the data lifecycle, which is here on the right side, the data lifecycle. And very often when it comes to publishing results, maybe in repositories, it's a bit difficult. I mean, there's the machine, we produce data, then there's the repository, but in between there is the researcher, and she's not very often, not necessarily the fun part of her or his work to put these data also into repositories. And then there's a lack of support of platform tools, and this is something we want to solve here in this NFDI4Earth. So our key goals coming from these issues just described is we want to have a one community approach to sustainable, open, and fair research data management in system sciences. So we really try to get everyone on board. So this is not a top-down approach we have, but it's a bottom-up approach we have. And for this, we have a couple of tools how researchers can participate. And I will show you these tools a little bit later, because I think these are one of the most important instruments we have in the NFDI4Earth and on which we rely, and which is actually also a large chunk of money we spend on. So this means community-driven agile development of platforms for data integration, collaborative data analysis, and so on. We want to have qualification for people to produce data tools, services as a basis for fair research data management. And we want to facilitate all this through something we call a one-stop for all. Now, the one-stop for all is basically a web page through which you can access everything. So think of Google maybe. It's also just a web page, but it was a game changer and still is. So because through search engines such as Google or DuckDuckGo, whatever, we get access to what we want. And this is basically what we aim for, to have one single web page through which you can access and reach everything you need in the domain of the Earth system sciences and related to data and everything around data. Now this, I hoped a little bit. I have to admit that we, by November, because this was the initial plan, had released this one-stop for all, so I could really show it to you, but unfortunately we are a little bit later, so we have a soft release later this year and a hard release then early next year. Otherwise, it would have been, of course, even nicer to really demonstrate this one-stop for all. I have seen some pre-release and it's really very nice. I can assure you of that. And one of the things is, with this one-stop for all, we also have a user support network so that it's not all just digital, all just web pages you are directed to, but if there's something you really don't get an answer through the one-stop for all, there's a user support network behind it, and you are directed to a human person who then tries at least to answer your question. And with this approach we have here, we hope also maybe to be a key driver of the build-up and operation of the entire NFDI, or bringing our part into it. Of course, other consortia certainly also have some great ideas to incorporate. These are sort of the ones we have a little bit here. So from an individual user's perspective, a user, so she goes here, a researcher, a student, so to do one-stop for all. Hopefully she gets her answer there already via one of our products we have. I will come to these products. Otherwise, she's directed to the user support network, and this is then contributed by participants of the NFDI4Earth here. So this is something we are currently building up. So I'm briefly going into this concept we have, not too much, because these charts are always a bit hard to memorize. So what we have, so this is again this one-stop for all here in the center with the user support network, and then we have something like a living handbook. So this is actually what we do here in Frankfurt. This is our responsibility, the living handbook. So this collects articles about, first of all, the outcomes of the NFDI4Earth itself. But also then, for example, maybe you need a data management plan for your next proposal, and you don't know what a data management plan is. So there will also be, hopefully at some point, then an article about the data management plan in the living handbook. So you can go there, find this resource, how to write a data management plan for the Earth system sciences for my next proposal in here. Another one is the knowledge hub. And as I said before, so maybe there are lots of data, or there are lots of databases, small, large ones, and the knowledge hub collects all these databases that are available. So then you can access them and find really them through collaborative analysis tools and so on. Now, one of the really core products, and I want to go into this a little bit, is this part, because this is how everyone can really participate and provide important input to the NFDI4Earth and participate in it. And I will show you this a little bit more detail. So we have pilots. The pilots are one-year projects. So you can apply at the NFDI4Earth for such one-year project. So this is full-time equivalent. So it is about 75,000 euros you get to conduct one research data management question. So of course, this should have a relation to the NFDI4Earth. So we had, for example, something about data cubes, something about metadata, vocabularies, ontologies, some model integration. And I will show you one example, which was part of one of the pilots we actually did, what came out of it, and just to give you some idea what is meant here. And the second round just started, and the next call will be live in 2024. In the first call, we had 14 pilots. In the second one, I think it was 7. Well, it depends all on funding. We have as well. But let's see how many we have next year. Another one are incubators. This is sort of similar to pilots, just shorter. So you have 3 to 6 months you can apply for, also full-time equivalent. So this is then maybe something between, I don't know, 15 and 30,000 euros you can apply for. And this is more high risk. So if you have really want to try out something, if you have an idea and you want to try this idea, you can apply for an incubator and then you get 3 months or 4 months or something like that to try out your idea, see how it works, and depending on this, maybe apply for a pilot, apply for a DFG proposal, something like that. Second round also just started, so next call will be in 2024. Then you have education and training services. So this will be, this is a platform for sharing educational material. And here again, I'm not going through all this. Here again, we have some pilots. So this is basically twofold. One part is that people can upload or provide their learning material, maybe videos, maybe scripts, whatever, through a portal, a training portal of the NFDI4Earth. And if you maybe want to build something, say you want to make a couple of videos and you need some support, you can apply for an educational pilot here and you also get funding. And this is on a continuous application, so you can apply for this anytime. So there's also contact, but all the contacts are, of course, on the NFDI4Earth website. Then we have the Academy, and the Academy is for young researchers. So it's an early career training network, peer mentored environment, open academy program. And we have the first year cohort. And now we are currently, the application is open until 30th of November, in case someone would be interested, for the second cohort. And this is basically, these are, I think, 35 at the moment, young researchers from everywhere over Germany. And then they come together, and this is then funded. So these meetings they have, these are basically funded to exchange about data science in general, present their projects, make a hackathon, something like that. So this is also really a very great instrument here. And finally, we have something that's called interest groups. So these are the currently operating interest groups on research software, machine learning, long-term storage and archiving, and a couple more here. And this is if some researchers have a certain contribution they want to make to the NFDI4Earth, they can form such an interest group where they define maybe a standard, produce a white paper about something, and this is then a means of doing this here. So this at the moment has no funding because we thought it's not entirely necessary, but if some funding would be required for, I don't know, maybe a meeting or so, this might be also a possibility here. So these are the means of participating in the NFDI4Earth, and as I said, I think this is really one of the great aspects and instruments we have here at work. So our strategy looks as follows. Please don't have a look at here in detail. I just want to point out that we are here NFDI4Commons, so this should be my name. It is an old one. Forgot to change this here, so I'm responsible for this NFDI4Commons theme here. And as said before, we are responsible for the Living Handbook, and as we are responsible for this, I thought I could quickly just show you 3 or 4 slides about how this is working, what we are doing. So what is the Living Handbook? It is essentially text-based information with articles, but of course can include media like images, like maybe a table or video or something like that. We are even ambitious, maybe can include some Jupyter notebooks in the future, but this will not be an option when we start in the next couple of weeks with this. And the structure is that we are a wiki-like encyclopedia. So anyone can submit an article. The article can be changed, can be updated. Someone else can add something to the article, but it can also be a white paper. So where there's no change after the publication of this white paper, of course. It's possible to have collections. So if, again, maybe you have a data management plan about your system sciences, it might be in the collection of the data management plan, where there's another article about how to write a data management plan, how to upload or whatever data management plan. But could also be one of these articles in another collection only about proposal writing or something like that. It is partially peer reviewed, so if necessary, it will be peer reviewed if it's a white paper or if it's a really article about some specific, I don't know, maybe vocabulary or something like that. So if someone suggests vocabulary for rocks, then this would likely be peer reviewed, so to make sure that this is not nonsense that's submitted here. And everything is curated by an editorial board. And everyone, again, as it is a community approach, if you would be interested in joining the editorial board, it would be possible. That's what's said here. So it's community-driven content. Initial set of articles currently prepared. We have about 100 articles right now. Many of these are, for the moment, outcomes of the NFDI4Earth. For example, the outcomes of the pilots. So if you're interested, what are these pilots? What have they done? You can find these articles in the Living Handbook, also for the incubators or from the Educational Hub. And here, so you could submit your article directly here. Of course, once the website is live, this will be a button that you can click and not this cumbersome email address here, or you can just ask me. Now, this is about for the NFDI, and then this is just touching on Jupyter Hubs, because we initially thought about, as said, in conjunction with HeFDI, maybe to work on a Jupyter Hub. Now, this changed a little bit, as this is a fast-pacing area here. So it was always thought that the NFDI should have some basic services, something like an authentication service, something like EduRoam or something like that. And it was not clear until recently how this would be realized. And then the idea was to, as one consortia, have, that is a little bit different from the others, have one that provides these basic services. And this consortia is called Base for NFDI, and it is now also funded. And now services can apply for being incorporated in the Base for NFDI basic services. And one of these services that's currently under review, as far as I know, is, for example, Jupyter Hubs. And there are some big players from Germany who participate there. And then we thought, well, it does not make a lot of sense to also try and set up a Jupyter Hub if we now have this as a basic service. So the need sort of disappeared here. So we will replace this a little bit by some new developments, which is making web applications. And there's currently, and with this I'm coming to the last part of my part of the presentation here, which is the outcome for pilot. And I would like to show you one of such web applications that we built and that has a direct connection to research data management. I'm going through this rather briefly. So this is about, so this is a web application. So I'm now live in the browser. And so think of, you have a lab and produce data. And now these data come out of the machine in a not very nice format, but you want to provide it in a more nicer format. So what you can do then is you can store it, for example, in an electronic lab notebook. And 4 weeks ago, there was a presentation by Michael Selzer, very nice, about CADI-Format. And actually, we use CADI-Format here. So we use an electronic lab notebook. So all the cumbersome data that come out of the machine go into this electronic lab notebook. And I'm not showing this here. Michael showed this 2 talks ago. But now switching to Tamanna, and thank you, and please, Tamanna, go on with your part.
Thank you, Dominic. All right, so good morning, everyone. I'm Tamanna, and the topic for my talk today is automated classifications of rock using machine learning. So to begin with, I would like to give a brief introduction about our field of study. Geology is the scientific study of Earth's structure, composition, and history. It plays an important role in understanding our planet's past and predicting its future. Igneous rocks are one of the 3 primary rocks that are found on Earth, and they originate from the solidification of the molten rock, which is known as the magma. They are of 2 types, intrusive and extrusive. Intrusive igneous rocks are the ones that form beneath the Earth's surface with slow cooling, and they result in coarse grain textures, as we can see here, for example, diorite and granite. Whereas the extrusive igneous rocks are the ones that form on the surface with rapid cooling, resulting in fine-grained or glassy textures like basalt and andesite. So we generally classify them on the basis of major element oxides, for example, silica oxide, aluminum oxide, iron oxide, etc. So this is a classical method for rock classification, and this plot is known as TAS plot, total alkali silica plot. It is the fundamental and most widely applied tool in petrology and geology, and it is used to classify extrusive rocks based on the composition, as you can see, a lot of rock types, and it is also instrumental in understanding the differentiation of magma. So on the x-axis, we have the silica oxide, and on the y-axis, we have the sum of two alkali oxides, sodium and potassium. So for example, we take the study of basalt. For basalt, the silica value ranges from 45 to 52 weight%, and the sodium and potassium ranges from about between 4 to 6% weight%. So what is the aim of the study? So as we know that the volume of geochemical data has exponentially increased over the last few decades, machine learning techniques can efficiently be used to handle and process large data sets and make it possible to derive valuable insights from extensive archives of historical data. So we aim to discern previously unrecognized correlations in the already existing databases within the geological evolution of rocks, and also look for correlation or groups within the same field, for example, the basalt field, as I mentioned in the last slide, and thus expand the scope of knowledge in our domain. And as we know that machine learning is able to provide more comprehensive data analysis and has better results to an extent. There has been a lot of work that has been done in geology using machine learning, and these are the various areas where machine learning has been applied. For example, the lithology classification. The identification of lithologies, source of materials, special geological events, mineralization zones, etc., are the are the basis of the Earth science. So, using machine learning, using inputting the image data, the model was able to recognize different rocks from igneous, sedimentary, and metamorphic rocks. Second, we have the mineral classification. McVendy in 2016 was able to create a model to identify magnetite in hydrothermal and metamorphic volcanology massive sulfide deposits. Also, a lot of work has been done using the image data to classify various minerals as seen under the microscope as well. Recognizing ore deposits, researchers these days are also exploring feasible machine learning methods on digital mapping. So using neural networks, one can predict the hydrothermal gold and silver deposits, and it had an accuracy of more than 70%, and it has been tested in the area of Iran. And anomaly detection. So a hybrid machine learning model with the k nearest neighbor regression and random forest were able to classify zinc and lead anomalies, and they were also able to classify the grades of these anomalies. They were further correlated with the mining activities and drilling data. And the last, using the databases, classification tree models were developed to distinguish basalt from different tectonic settings using neural networks. So there are two types of learnings in machine learning, and these are supervised and unsupervised and supervised. So I will take you through the major differences between them. So first is the labeling of the data. In supervised learning, the data is not labeled. For example, as you see here, I have inputted the major element oxides, but I do not mention the name of the rock this data corresponds to. Whereas in the supervised learning, I have same major element oxides. However, in this time, I will also mention the rock type or the rock name each data corresponds to. And the goal of the unsupervised learning is to discover hidden patterns, whereas the supervised learning is rather used to learn a mapping or relationship between input features and their associated target values and then make predictions. The task type for unsupervised learning is mostly clustering, which is grouping data points with similar features, and dimensionality reduction, which is reduce the number of features, whereas the task type for supervised learning is mostly classification and regression, which is predicting the continuous values. And since the data is unlabeled, there is no human guidance required for unsupervised learning, whereas we have to label the data in the supervised learning. So human guidance for training the model in supervised learning is important. And due to all the above reasons, the evaluation in unsupervised learning is more challenging and subjective, whereas the supervised learning model, the accuracy can be checked. So these are some preliminary results of my model, and the plot presented here represents the output of a variational autoencoder, which is a generative model. They are used to learn the features on the basis of probability distribution of the data. In this visualization, we observe the presence of 10 distinct clusters. When examining the two probability distributions I reduced my data to. So the clusters indicate that the model has successfully learned and separated different patterns or groups within the data itself. And these are the results of my supervised learning. I inputted 10 different types of rock data here again, but with labels. And this time the model was able to distinguish 92% with an accuracy of 92%, which means like out of every 1000, out of 1000 samples that were predicted, 915 were classified correctly. So to carry on this machine learning model, where was the data? What was the data we used? So we gather data from the online portals, GeoRock, OsGeoChem, PetDB, and OnePetrology. GeoRock is a comprehensive resource for geological data, and the available data is collected from wide range of sources. The databases can be downloaded on the basis of rocks, locations which include various tectonic settings, and also minerals and inclusions. PetDB is the petrological database of the ocean floor. It offers a wide range of information on the composition and characteristics of rocks, minerals, and fluids. As you can see, the data can be downloaded on the basis of location, features, sample type, chemistry, etc. OsGeoChem is an initiative by the Geoscience Australia that provides access to geochemical data across the Australian continent. It is a comprehensive repository and geological and geochemical information. OnePetrology is one of the nodes of the Deep Time Digital Earth, and it is responsible for construction of database of magmatic rocks in the website. Data can be chosen from various options like igneous rocks, zircon data, isotopic data, as well as particular data just from the China region. For our analysis, we also created a fake random data set within a Jupyter notebook using Python. And the primary purpose behind the generation of fake data was to access and validate the functionality and precision of the ML, of the machine learning model that was developed. Additionally, this endeavor sought to evaluate the model's performance when exposed to novel data, while also ascertaining the effectiveness of the model in accurately grouping the data. So these are the results of the fake data of the machine learning, and this is the same task plot as we saw earlier. So the green dots indicate the correct classifications. The model was trained on the databases, the data that was from the databases, and it was tested on the fake data. So here we see also the accuracy increased from 92 to 94% when tested on fake data. And when we see the misclassifications of the rocks, we generally see the misclassifications are either on these boundaries or the intersections, meaning intersections of 4 different type of rocks. And also we see the major misclassifications are between basanite and tephrite. So accuracy from 92 to 94% increase. This means there were some misclassifications in the original data as well. So for data access, while gathering the data, there were some challenges that we had to face, and that was the data was available on different portals. A lot of data was available actually, and for A, which is accessible, some of the portals have an API while others not. So so it was pretty difficult to for each and every portal to get data. And for I, which is interoperable, they all the portals lack common vocabulary. So if one of the portal follows a certain format, the other had a completely new format. So And when I collect all the data and then I had to use it to my machine for my machine learning model, I had to create an entirely new database out of all the databases I downloaded. So the lack of uniform formatting across all the data portals posed significant challenges, particularly in terms of interoperability and adhering to the FAIR principles. This hindered the ability to make data accessible as well as interoperable across different machine learning models, and it affected the efficiency of data retrieval. So now initiatives by HeFDI and NFDI4Earth are there to centralize these databases so that databases are found at one portal, and which will further help in using this entire data for various machine learning models in the future as well. Thank you for your attention.
Thank you very much to both of you.